So now that we understand what collision-resistant hash functions are and we know how to construct them, we're ready to describe a very popular MAC called HMAC. So let me remind you what the Merkle-Damgard construction is. Basically, we have a small compression function h from which we build a large hash function which is collision-resistant, assuming the compression function is collision-resistant. The question we're going to ask this segment is, can we use the large hash function to construct a MAC directly without having to rely on a PRF? So here's the first thing that comes to mind. Suppose I give you a Merkle-Damgard hash function. So you notice it hashes large messages into small digests. And we want to convert that directly into a MAC. So the first thing that comes to mind is, well, why don't we just hash the concatenation of the MAC key along with the message that we're trying to MAC? And it turns out this is completely insecure. And so let me ask you why this is insecure. The answer is the standard extension attack. And if you think back to the Merkle-Damgard construction, you realize that if I tell you the tag for a particular message, in other words, I tell you the value at this point, it's very easy for the attacker to just add another block and then compute one more application of the compression function h, and now they will be able to get the tag for the original message, concatenated the padding block, concatenated their word w that they added themselves, and as a result, this is an existential forgery. Yeah, so basically this is exactly what we get here, where after concatenating the padding block, the attacker can actually concatenate whatever he wants, and he would get the tag on this combined message. So this is totally insecure, and I cannot tell you how many products have actually made this mistake, where they assume that this is a secure MAC. This is completely insecure and should never, ever, ever be used. Instead, there's a standardized method to convert a collision-resistant hash function into a MAC, and that method is called HMAC. So, in particular, we could use the SHA-256 hash function to build this MAC. The output is going to be 256 bits, and in fact, HMAC is believed to be a pseudo-random function. So, in fact, out of SHA-256, we get a pseudo-random function that outputs 256-bit outputs. So let me show you the construction. Here's the construction in symbols, and it works as follows. First, we take our key k, and we concatenate what's called an internal pad to it, an IPad to it. This makes it into one block of the Merkle-Damgard construction. So for example, this would be 512 bits in the case of SHA-256. We prepend this to the message m, and then we hash. Now this by itself, we just said, is completely insecure. However, what HMAC does in addition, it takes the output, which is 256 bits, it prepends to that the key again, XORed with what's called the outer pad, the O pad. This also becomes 512 bits, it's one block, and then it hashes the combination of these two to finally obtain the resulting tag on the message M. So it's more, rather than looking at this in symbols, it's more instructive to look at HMAC in pictures. And so you can see here are the two keys, K XOR inner pad, which is then fed into the Merkle-Damgard chain, and then the resulting output of this chain is fed into another Merkle-Damgard chain, and finally the final output is produced. Okay, so this is how HMAC works in pictures. And now I want to argue that we've already seen something very similar to this. In particular, if you can think of the compression function h as a PRF, where the key is the top input, then what we're actually doing here is we're evaluating this PRF h at a fixed IV, and therefore the result here is a random value which we're going to call K1. And then we apply the Merkle-Damgard chain, and we can do the same thing on the outer pad. If you think of little h as a PRF, where the key is the upper input, again we're applying this PRF using a different key to a fixed value IV, and as a result we're going to get another random value K2. So now when we compute HMAC using these keys K1 and K2, this should actually look very familiar. This is basically NMAC. It's identical to NMAC that we discussed in a previous segment. And notice, to argue that this is an NMAC construction, we have to assume that the compression function little h is a PRF where the key is actually the lower input to the function. Now let me say that these pads, the IPad and the OPad, these are fixed constants that are specified in the HMAC standard. So these are literally just 512-bit constants that never change. And so when we go back to look at the complete HMAC construction, you realize that the main difference between this and NMAC is that these keys here, since they're dependent, you notice they're both just the same key XORed with different constants. Essentially, the keys K1 and K2 are also somewhat dependent because they're computed by applying a PRF to the same fixed value, namely IV, but with dependent keys. And so to argue that K1 and K2 are pseudo-random and independent of one another, one has to argue that the compression function not only is a PRF where when the input, the top input, is the key input, but it's also a PRF when dependent keys are used. But under those assumptions, basically the exact same analysis as NMAC would apply to HMAC, and we would get a security argument that HMAC is a secure MAC. And so as I said, HMAC can be proven secure under these PRF assumptions about the compression function H. The security bounds are just as they are for NMAC. In other words, you should not have to change the key as long as the number of messages you're macking is smaller than the size of the output tag to the 1/2. But for HMAC SHA-256, the output space is 2 to the 256. Square root of that would put us at 2 to the 128, which means that basically you can use HMAC SHA-256 for as many outputs as you want, and you'll always maintain security. And as a last point about HMAC, I'll tell you that TLS standard actually requires that one support HMAC SHA-196, which means HMAC built from the SHA-1 function and truncated to 96 bits. SHA-1, remember, outputs 160 bits, and we truncated to the most significant 96 bits. Now you might be wondering, remember we said before that SHA-1 is no longer considered a secure hash function, so how come we're using SHA-1 in HMAC? Well, it turns out it's actually fine because HMAC, the analysis of HMAC, doesn't need SHA-1 to be collision resistant. All it needs is that the compression function of SHA-1 be a PRF when either input is allowed to be the key. And as far as we know, that's still correct for the underlying compression function for SHA-1. Even though it might not be collision resistant, as far as we know, it's still fine to use it inside of HMAC. So this is the end of our discussion of HMAC, and in the next segment we're going to look at timing attacks on HMAC.